Okay, I'm going to try to walk you through how to set up a chi-squared test of independence in Excel. This one is harder to do as a specific layout because the grid really depends on how many different groups you have. But so let's use an example where we look at the distribution of different kinds of coins, either in the pockets of clothes in my house or on top of bureaus. So we would have one category which is coins, and that's going to be pennies, nickels, dimes, quarters. And then we would have locations. Insert another column here, locations. And that's going to be pockets, or what was the thing I was going to say? Bureaus. Sweet. Piggy bank. We'll do piggy bank too. How about that? All right. So let's say that mostly when I'm getting coins, if I'm paying in cash, I leave the pennies in the take a penny case. So I have no pennies and coins. Over the course of a week, I might accumulate 10 nickels, 10 dimes, and I would particularly hold on to quarters. So let's say I have 20 quarters in all my different pockets around the house. All right. Now bureaus, let's say that all coins just sort of get randomly left there, but then I go back and pick out quarters when I need them to do laundry or parking. So we might have 20 here, 20 here, 20 here, and only 2 there. And then the piggy bank, maybe we'll have a similar sort of pattern, but with pennies also maybe accumulating more. So we have 30, 25, 20, and 10. So we'll say we're descending. So we've got 3 different groups for each of those. So these should not, since they're not the same proportions in each of these, then we would not expect us to have a 0. We would expect this to be a significant chi-square test of independence. So we set this up. So our next step is to compute the marginal totals. So we do total equals sum, and there we go across. Fill that down, and then we do equals sum over here. We sum those, and I'll do magic fill just for variety's sake, and there we go across. So there are 187 of those, and let's double check by selecting all of these, and then looking down here, we see 187, so that works. Great. So these are our observed values. So the next thing you do is you copy all that. Whoops. My control key's not working because of soup. Observed. Paste it down here. And now we change this to expected. And then we change this to equals the total number of pockets times the total number of pennies divided by the grand total. And that is the formula for calculating our expectancy. So it's how many, since the pockets row here, the pockets row there, the pennies column here, the pennies column there, and then the total. So we need to use some dollar signs here. This blue one is always going to be in column G, so we put a dollar sign from the dollar there. So red one is always going to be in row 6, so we put a dollar sign there. And then these are always going to stay constant like that. So we hit enter, and then we magic fill across, and you can see the row moved across, but since the column changed for the red one, but not the blue one, and vice versa, here come my kids, that's going to be noisy, and so we paste those there, and look, the marginals stayed the same, but now the insides are different. So now we can do the chi-squareds. Aren't my children precious? Okay. Chi-squared
No, you are not fooling me. Nuh-uh.
That is hilarious that that's going on while I'm trying to give a lecture here. But yes, I cleaned the bathroom. Don't sound so surprised. So we do chi squared. And now we're going to do equals the observed minus the expected divided by the expected. So we copy that. Now we don't need any dollar signs because it is a direct match. And now see our sums. That's the sum of all those, which is what we want. And here's our total chi squared. So we got a chi squared for each of these rows, chi squared for each of these columns, and the total chi squared. So then we can do our statistics. So our degrees of freedom is the number of locations minus 1. So it's going to be equals 3 minus 1 times the number of columns. So there's 4 of those. We're not counting the total column, right? So that's 4 minus 1. So we've got 6 degrees of freedom. And our chi squared value is this one right here. And then our p-value equals chi square dot dist dot right tail, because we want to know what the probability of observing a chi-square value this big or bigger is if these values and these values are actually independent of each other. There's our degrees of freedom. That's going to be like some giantly small number. I put that in the wrong thing, so move that over there. So that's 7 in a billion, so that's pretty small, p-value. So we would say there is a significant association between coins and locations and then we say chi well, I'll just do that. Chi to quote and this equals and quotes another and round that. You can usually round that to the nearest 2. And comma p, and if this is less than, well, you know, we're just going to put p is less than 0.01. There we go. Oops, I forgot quotes. There we are. How's that for you? Make sense? Now, if these were all just random numbers, so let's duplicate this. We'll create a copy. And so then we'll say, let's just pick a random, so not significant. So we'll just pick a random number between 1 and 20 for each of these. So equals rand between. Copy that. Paste that. Well, that's irritating. That's hilarious that it ended up still being significant. Huh. That shouldn't work. Oh, maybe I'll do rand between 10 and 20. Okay, I mean, close to 1 is too small. Haha! There we go. That worked. Yeah, so 1 and 20 was too small, but between 10 and 20, they're all the same. And there we have our significant. Why is this being obnoxious? There we go. Our non-significant, so there was no P equals change that equals and round this to 3 digits and delete those and it'll look like that. Fabulous! Alright, so that was twice as long as it should have been, but hopefully still intelligible.